Hey, Mike, you hearing us okay in Kingsport?
Yeah, you're good, bud.
All right, thank you.
Holding here, I don't feel sleepy, but I was really sleepy Tuesday.
Yeah, it was important. So our first thing is homework 6. That's going to be for this coming Tuesday, and the date is the 16th. Now, I went back and picked some homework problems. I went all the way back to chapter 15, 15, 16, 15, 18, 15, 22. Now, look, these are all multiple choice. Remember, I'm underlining them. I want to make sure you remember what the central limit theorem tells you, what the law of large numbers tells you, and whether you can pick out what's a parameter of statistics in a little problem. And then I picked 1531. If I was you, I would look at my notes and see that me and you did in class. We did problem 1530. This is very, very similar to that. And what I'm expecting to see out of 1531, because this is one of the ones where, you know, you're either looking at one at a time or you're looking at n at a time. I'm expecting to see z-scores. And I'm expecting to see something like, you know, you wanted the probability of whatever, and then tell me what it's equal. I don't expect you to draw all the pictures, but you're going to have to do some z-scores in 1531, and then you're going to have to tell me, you know, okay, the problem asks for this probability, and this is what I get by using table A or whatever I want to use. Chapter 16 is about confidence intervals. Those 3 are multiple choice, just to kind of get you started with everything. And then 16, 19, I ask you to read a problem and calculate a confidence interval for me. Chapter 17 is our test of significance. Again, all these first ones here are multiple choice, right? So the way I see it is all these ones I think I give you multiple choice this time, they're mostly like you're reading them, you're going to answer. There's nothing to calculate for you. I can remember off the top of my head. And then 17.28, that is a test of significance where it asks you to state hypotheses, calculate your test statistic, find your p-value, make a conclusion. And actually, that one is connected to that one. One of them is a confidence interval where you're trying to estimate mu in 1619. And in 1728, they're making some claims about the population mean mu, and you're going to do a test of significance. And then the chapter we're going to talk about tonight, chapter 18, I got 18, 19, 21, 22, 24. These 4 definitely is, I can remember for sure that you're just going to read and pick out what the multiple, there's nothing to calculate, it's reading and do you understand what's going on here? And then there is one calculation here, and it's 1842. We will do a problem tonight out of chapter 18. It looks very, very similar to 1842. Are you counting them? Don't count them. No, look at the ones that don't have any lines under them. 1, 2, 3, 4. Well, because I promised, I'm pretty sure all the ones that are multiple choice, you're going to read through them and just answer whatever it is, right? So there's no calculations there. The ones that are not multiple choice are the ones where you do a calculation, right? That's the way I wanted to do this. How many's on there? 18. Well, look at it this way. We're almost done. So there's homework 6, and I see one more in our future. All right. Then the other thing we need to talk about is the capstone project. We're on number 5. Now, there's 2 numbers 5. There's 5T and 5H. It should have been it won't matter. Look, you're going to do 5T. If the sum of the digits in your E number is an even number, in other words, you're going to add up all the digits. If you get an even number, right, you're going to do this one. If you take the sum of your E number and you get an odd number, you're going to do 5H. I would appreciate whichever one you don't do, because you just like wipe that one out. Okay? They're both very similar. Actually, the questions are kind of the same, except, you know, the variables change. Both of these problems 5 are about 2 categorical variables. So they're about a 2-way table and so on and so forth. 5T says wall and abortion. Question 14 from the survey asked students, do you support the idea of building a border wall between the U.S. and Mexico? Possible answers was a yes or no. Question 15 asked students, would you identify yourself as pro-choice or pro-life? Obviously, the two answers are pro-choice, pro-life. We want to check if there's a relationship between wall and abortion. In other words, we want to check to see if there's a relationship between these two categorical variables. Assume the students who took the spring 2019 survey are an SRS, obviously. Everything me and you talk about is going to be a simple random sample. Now, here's the deal. I've got two categorical variables. And in the big scheme of things, what we're interested in this problem is there any relationship between them? I got wall and abortion. It says create an appropriate graph to display the relationship between wall and abortion and insert it here. This is a cluster bar graph or a segmented stack bar graph. Here's what I would think. Normally when I am looking at two categorical variables, I always like to think about does one help explain or influence the other. Right? Remember, I want to treat one as, what I want to do is, I want to treat one as the explanatory variable and the other as the response. I have a little difficult time with this one, but here's the way I would attack this. I got this weird thought of what you think about abortion helps explain or maybe influences, actually helps explain what you think about building the border wall. So I'm going to treat abortion as your explanatory variable and the wall as your response. The reason for me doing that is, when I come over here, there's my file and all that, I need to make a graph. My graph is going to be a bar chart. Again, I have counts of unique values, right? Nothing summarized for me here. I want cluster, because that's the one I do when I want to look at these conditional distributions. And I want to click OK. I think I want to click OK. Okay, yep. Now it wants to know, okay, where's my categorical variable? Remember, the one you put in first is your explanatory variable, and the one you put in second is your response. I want to put abortion in first, then I want to put wall. I also want you to do one other thing here because I like to see these cluster bar graphs in terms of the bars being percentage. I like chart options, show y as a percent within categories at level 1. Me and you did the same thing in chapter 6 when we made these cluster graphs, cluster bar graphs. If I click OK, and I click OK, oh, let's do this again. All that's the same. I want to put in the wall and then abortion. I still want to make sure show y as a percent within categories at level 1. So what I should be looking at is two conditional distributions about how you feel about abortion, given what you're going to tell me about the wall, right? Look, I've given you both of those, and either one of them, I would have been happy with either one, right? Either set of these, where I'm looking at the two conditional distributions of abortion, given what you said about the wall, or the one I had up before, the two conditional distributions of what you said about the wall, given what you said about abortion, they're both. I can't really, that's the reason I'm thinking hard, is because I don't really have one thought or the other about one explaining or influence the other, all right? I would take this one too, okay? This is the guy you're going to take and you're going to put over here. Over here, right? Create a graph. There's my graph. Hey, let me ask you a question before we go any further. Do you think it makes a difference on what you think about the wall and what you think about abortion? See, there's two conditional distributions here, right? There's the conditional distribution for abortion for the people that said no to the wall. There's the conditional distribution for abortion for the people that said yes to the wall. Do those two graphs look the same or they look different? Folks, this is as different looking as they get. Notice the ones that said no to the wall, a very high percentage of them are pro-choice. The ones that said yes to the wall, a very high percentage of them are pro-life. Any ideas, just off the top? I mean, look, I'm just thinking here. What are we really separating out by? Democrats and Republicans? Oh, I know that's not one of my categorical variables here. So we're not going to ask you, do you see a relationship here? I'm pointing out to you, yes, you do. It does make a difference on, how you feel about the wall and how you feel about abortion. There is a relationship between how you feel about the wall and how you feel about abortion, right? If you are more likely to support the wall, you're more likely to be pro-life. If you're more likely to be against the wall, you're more likely to be pro-choice, all right? It doesn't ask me that. It just tells me to take that over there and put it there, all right? So that's what you're going to do. Then it says create a two-way table. Meaning you've never created a two-way table. We're going to here. So I'm going to go to, it tells you where to go. I'm going to go to Stat, Tables, all right? And I'm going to go to Cross-Tabulation and Chi-Square. Our main thing here is cross-tabulation. I'm going to click OK. I need to put, look, I've got the raw data here. I've got the actual data. I need to put one of the variables as the row and the other one as the column, and nobody cares which way you go. I'm going to put the wall as the row and the abortion as the column, and I've got everything I need here. I'm going to click OK. Folks, that's like all the two-way tables we would have made and seen in Chapter 6. Notice the row variable is what they think about the wall, yes or no. The column variable is what they thought about abortion, pro-choice, pro-life. There are 635 people in the table. That's a two-way table where the columns are summarized, the rows are summarized, right? That's a nice one. That's the table you need. Again, you can flip-flop the rows and columns. Nobody's going to care. You're going to get the exact same answers on these other questions. You're going to take that, you're going to put it in B. Then it says, suppose we select one student at random. Here comes probability questions from a two-way table. Part C says, what's the probability the student supports the idea of building a border, said yes to the wall, and is pro-life? Who are we looking at? They said yes to the wall, and they're pro-life. Does everybody see there's 184 of them? Yes to the wall, pro-life. I'm believing you're looking at the end. You should take 184 divided by 635. Okay. Part D, what's the probability that the student supports the idea of building a wall, yes to the wall, or is pro-life? So they chose, what's or mean? It could be this one or that one, right? So, you remember we did this with the two-way table in class when we did chapter 13, I think it was? I'm going to take all the ones that say yes to the wall. I'm going to take all the ones that said pro-life, and I'm going to subtract out the ones you counted twice. Which ones did you count twice? The 184, right? You counted them with the yes. You counted them with the pro-life. You need to add that row, that column, subtract out 184, and what are you going to divide by again? I can't tell you. You've got to divide by 635, right? And then part E is our third type of probability question. What's the probability this student does not support the idea of building a wall, said no to the wall, given that the student is pro-life? You're only going to look at pro-life. You're only going to look at the second column, right, of which there's a total of 305, and then be careful, right? They don't support the wall. You want to know what's the probability you chose someone out of that group that said no. Out of the it didn't say pro-life, didn't it? Given the students pro-life. I'm going to look at the pro-life column. 121 said no, out of the total of 305. Well, hell, I did all three of them for you. Sorry. Okay. Part F, we can't do yet. So there's a bonus to here. Right? I can't do this yet. This will be the last thing me and you do on the capstone project is this bonus problem. This bonus part of this, right? I can't do it before you. Because there's a test of significance about a relationship between two categorical variables, and it's the last thing me and you do this semester. Now, if we go to 5H, we're going to change the variables. Question 2 from the spring 2019 survey asked, what gender you'd identify, female, male, or other? Question 5 said, do you prefer to read textbooks in print or electronic device? such as a smartphone, tablet, computer, or e-reader. So they gave you two options, in print, on an electronic device. Two categories of variables. We want to see if there's a relationship. Now, this time I actually do have a thought. I actually think that maybe your gender will help explain how you like to read the textbook. So I'm going to treat your gender as the explanatory variable and how you like to read the textbook as your response. Over here, I'm going to make a bar graph cluster, because the questions are exactly the same other than the two variables have changed. This time, I want to put in a person's gender, and then, what's the other variable? Textbook. So I'm going to be looking at the conditional distributions of how you like to read the textbook, giving your gender. And again, if you're coming in here the first time, make sure you show Y as a percent within category of level 1. There's my three conditional distributions, one for each one of the genders, and they're the conditional distributions of how you like to read the textbook given your gender. Are these three the same? Do they look different? I understand there's three of them because there's three genders here. These actually look different. Notice, the first two look similar. The third one looks completely different. Right? There's a higher percentage that said on electronic device than in print. The other ones were in print. Now, I don't know if that's actually going to be a significant relationship, but these three bar graphs do look different. Then, what do I need? Just like this problem over here, I'm going to need a two-way table. If I want the two-way table, stat, tables, cross tabulation. Put one of them in the rows. I say we put genders. Put the other one in the columns. I say textbook. You can do it either way. Nobody cares. And we click OK. There's your two-way table. Notice you've got 3 rows this time because of the 3 genders. You've got 2 columns. And again, you got 635. Everybody okay with that? So that's your two-way table. And then I can tell you what the 3 questions are going to ask you. The first one's going to be and, the second one's going to be or, and the third one's going to be a conditional probability. What is the probability that a student identifies as being female and prefers to read the textbook in print? So female and in print. How many are female and say in print? Does everybody see the 308? You're going to take 308 and you're going to divide by the total number there for that probability. Because there's 308 females that said in print. Part D, what's the probability that the student identifies as female or says they prefer to read textbook in print? Female or in print. What are we going to do? We're going to add up all the females, the first row. We're going to add up all the in print, the first column. And how many are we going to subtract out? How many did we count twice? It is our 308, correct? And we're going to divide by 635. The last one's a conditional probability problem. What's the probability that the student identifies as other, given that the student prefers to read the textbook on an electronic device? So we know they like to read on an electronic device, and then out of that group, what's the probability you chose a student that chose their gender as other? So where am I looking? On an electronic device. I'm looking at the second column. There's 155 there. And how many chose other as their gender? 3, right? So we're going to take 3 divided by 155. All right, one more time. What's the probability the student identifies as other, given that the student prefers to read a textbook on an electronic device? The electronic device is the second column, 155. How many of them are other? Chose other as their gender? 3 out of 155. It's going to be a very, very small probability of 3 out of 155, right? But that's how the calculation goes. And you're going, so why did you help me so much? Well, we need to be able to do this because this won't be the last time you see a two-way table and somebody starts asking you probability questions like that. And you're going, well, how do you know that? Well, I guarantee you on May 2nd, there'll be a two-way table on the test, and there'll be 2 or 3 probability questions right off of there that look exactly like what we're doing here. You know, can you do an and problem? Can you do an or problem? Can you do a given that a conditional probability? That's the reason those 3 are on. Now, I don't believe it'll be this two-way table. I don't know if it'll be this two-way table, or it may be two other categorical variables, but you've got to be able to calculate those three types of probabilities. And again, I can't do the bonus. I can't do the test of significance for a relationship here or no relationship. That's the last thing we'll do there. And I'll actually do both of these at the end of the semester when we're done. All right, so that everybody gets a fair shake. I don't want to not give everybody a fair go at it. Now, here's the thing about this chapter 18. All right? I'm going to talk about what I want to talk about, and you're going to actually read chapter 18. Now, I haven't asked you to read anything all semester. Have I? Have I? I don't think so. Right? So, I would like to talk about, I got about 3 things I want to talk about here, and I would like for you to read the rest of the chapter because you don't need me to understand the parts that I'm not going to say much about. If you read it, look, I didn't forget the thing I told you on Tuesday. You know, that homework problem to take a look at to see the connection between a two-way table and, a two-sided test and a confidence interval. Remember that one? I will come back and talk about that, not just yet. It's actually when we get to a certain type of problem on the capstone, I'm going to remind you and talk to you about it at that point. Okay? So, chapter 18. The title of it is Inference in Practice. Now, if I could say one thing to you here about this chapter, as long as somebody gives me a sample size, as long as somebody either gives me X bar or gives me the data, and I can calculate X bar, and as long as they give me sigma, is there anything stopping you and me from calculating a confidence interval or doing a test of significance? And the answer is no. So this is all about things you need to be aware of and cautions that there's nothing going to stop you, but then do you trust when you're done? Right? That's the point here. Now, here's what me and you have. We have 2 procedures. 2 inference methods. Confidence interval, test of significance. I've got some simple conditions. Yeah, I've written this down a few times for you. Anybody know what number 1 is? I'm going to say you do, you just don't want to talk to me tonight. That's always there, right? 2, we're supposed to be told that the population distribution is normal. And what I mean by that is, wherever you're drawing your sample from, that distribution where you're looking at, bless you, the value of the variable among all the individuals one at a time, it should look like it's normal. And then the third thing is, what separated all this is, when I say no sigma, sigma is given in the problem. Right? Think about all the problems I've done, all the confidence intervals, the test of significance, sigma is always given to me. Now, just for the sake of things, the confidence interval for mu, this is my formula. We don't memorize it. Remember, n's your sample size, sigma is that standard deviation of the population, x bar is that statistic, your sample mean. Where does z star come from? It comes from the confidence level C, and it comes from table C. The test of significance does this. I'm going to say it like this. We're going to test the null hypothesis. And it's always a statement that mu is equal to some value coming from the problem. The reason I'm going to say that's what we're going to test is because, we assume the null hypothesis is true to get us started. We use what I called on Tuesday the one sample z-test statistic, folks, it's a z-score. This guy right here. Right? That's the z-score I used on Tuesday. These are called z procedures. Okay, so why are they called z procedures? Well, there's a z-score as your test statistic. There's this little critical value, this z star that comes from the confidence level. They both have z's in them. Right? So there's z procedures. And I know you're going, okay, so who cares? Well, they're not always z procedures with us. Next week we're going to talk about something that's not z. See, the thing is, z follows the standard normal distribution. Table A. The standard normal distribution is the one that's normal, centered at 0 with a standard deviation of 1. Now here's my problem. The reasoning I've given you about a confidence interval, you know that we're 95% or 99% confident, the true thing you're trying to estimate is in there, that's not going to change no matter where I'm at. The p-value, what it tells you, remember the smaller the p-value, the stronger the evidence against the null and in favor of the alternative, right? The large values, p-values tell me that the data is consistent with A's not being true. It doesn't matter where we're at in doing this, the interpretation of your confidence interval and your p-value is exactly the same every time. So again, next week we're going to change another chapter. We're going to change our parameter and statistic. The interpretation is exactly the same. Okay? Now, I do want to look at a couple of things here. I'm on page 412 in your book. And right at the bottom of the page there, in blue, there's where did the data come from? You understand where the data come from makes a difference. All I'm going to do is come here and our methods are good when the data comes from a simple random sample. If it doesn't come from a simple random sample, we have issues. We also have issues if your data comes from a voluntary response, convenience sampling, self-selected, all that kind of stuff. Why? Because remember, those introduce bias. See, here's the thing. The confidence interval comes with a margin of error, doesn't it? I'm going to put your confidence interval up here. Remember, it's an estimate plus or minus a margin of error. The confidence interval comes with a margin of error. That margin of error does not cover bad data. In other words, if your data came from voluntary response, that's not included in the margin of error. The margin of error is there because of random sampling errors, right? Because we actually did a simple random sample. Any error that comes from bad data, voluntary response, convenience sampling, is above and beyond what the margin of error is covering. That's what the margin of error is doing, right? It's covering your random sampling errors, not voluntary response, bad data. Can I give it to you like this? You ever heard the story about if you put crap in, you get crap out? Oh, maybe that's just my old school thing. If you put bad data in, you're getting bad results out. The margin of error is not going to correct for it in the confidence interval, and there's nothing in the test of significance to correct for bad data. What I mean is data that's biased on something. All right? I was going to kind of leave it like that. You're going to read the rest of that for me, please. And while we're here, I'm going to give you a couple page numbers of things that you should look at. And there's on page 416. In the little box, it's just what I just said, but here's where it's written out in your book. The margin of error in your confidence interval, the z star times sigma squared n, doesn't cover all errors. It only covers random sampling errors. It does not cover any kind of undercoverage, non-response, biased question, bad data. It doesn't cover any of that. In other words, it doesn't fix those things. Okay? Now, I want to point that out to you. Go read that. Read this when you're doing the homework problems out of here, one of the multiple choice ones. Think about this, page 416, please. Okay? And then, the other thing I have is this. And I got a couple of thoughts about this little idea here. So now I'm talking about a test of significance, right? We always calculate our test statistic, we find our p-value. The question is how small a p-value is convincing. Well, the way I think about it is, if you're trying to convince people of something, change their mind about something they believe for a long, long time, how small a p-value are you going to need? You're going to need a very small p-value. Because remember, the smaller the p-value, the stronger the evidence against the null in favor of the alternative. Remember, the null is no effect, no difference. What's the status quo? What you have thought for a long time. If this is something people have believed for 50 years, you're going to need a really small p-value to change their mind. If you don't like that thought, let me give you this one. Let's say we work for a company, and we make some product where, okay, the average length of our product, mu, needs to be 10 centimeters. Right? The machine that makes our product, that makes sure that our length is 10 centimeters, is a $10 million machine. And if it's not doing what it's supposed to do, we're going to tell the boss he needs to get a new $10 million machine. Right? How much evidence do you want that the machine is not working correctly before you go tell the boss, we need a new $10 million machine? Do you want a little bit of evidence, or do you want lots of evidence? In other words, do you want a really small p-value? Yes. I always tell the students this. If you don't believe that little thought I just gave you here, when you're out there, and if you ever have that job and they ask you to do this, which is always a possibility these days, when you give the boss a p-value, let's say of 0.07, and say, look, you need to change out your $10 million machine, you only make that mistake one time in your life, because the next time you get a job, 0.07 won't be small enough. You'll be looking for 0.001 p-value before you tell the boss he needs a new $10 million machine. Does that make sense? Right? It's, okay, how much is it going to cost me to reject the null and accept the alternative? Or how much evidence do I need to have people change their mind about the null and accept the alternative? Again, if it's something they believe for a long time, it's going to take a lot of evidence. It's going to cost me a lot of money to take the alternative over the null. I'm going to want a small p-value. Here's another thing we do because we're standing in class. No sharp border. Now, we have to come up with answers one way or the other. And here's my thought. Let's say we do a test, and my p-value is 0.049. Let's say my significance level that I'm comparing to, remember we talked about this on Tuesday, maybe we're looking at the 5% level. Right? So in other words, the significance level, I wrote alpha, 0.05, the 5% level, what would you tell me at this point? You would tell me, statistically, significant. Why? Because your p-value is less than your significance level. Even though the difference is 0.001, we're sitting here in a class, we have to make a decision. The p-value is 0.049. 0.049 is less than 0.05, your significance level. You would immediately tell me, bang, you are statistically significant. Well, just for the sake of things, suppose we had done our test of significance instead of it being 0.049 in this class, what would you tell me at the 5% level? Well, this time, you are not statistically significant. Why? Because your p-value is bigger than your significance level. Because we're standing in the classroom and we have to come up with an answer. All right, is there really any difference here? Look, one time I'd have got 0.049. You're statistically significant at the 5% level. Another time I got 0.051. You're not. Is there really any difference between a p-value of 0.049 and 0.051? Yes, there's a difference. 0.002. There ain't no difference. All there is in the classroom. Is there a difference in the real world? Would all of a sudden, if we got these two different answers, would one time would we say, oh, yeah, you know, you're statistically significant. Next time, say not? In the classroom, yes, because we have to, you got to answer the question, right? In the real world, there's no difference between a p-value 0.049 and 0.051. We would tell whoever we were talking to, look, I can't make a decision here. We're too close to our significance level looking at it either way. We need to do the test over again. We need to collect some more data to see what happens. Maybe we'll get something different that's more clear where we can actually base a decision off of it. So far, so good. Now, all this stuff at the beginning here, you didn't need me to read this to you, talk to you about this, right? The next thing is, it turns out that there's this something called statistical significance. Now, that's based off the test of significance, and I would like to think about that versus practical significance. My first thought to say to you, these two things are not the same. Practical significance is real-world significance. Statistical significance is statistics. The test telling me whether something is significant or not. Practical significance is the real world. First, in red, so you won't forget. Not the same thing. Now, here's my thought. I'm going to write something down here, and I'm going to look at everybody for a second and see if you follow how I'm thinking about this. So, here's the deal. Sometimes the test can come back and tell me you're seeing statistically significant result. In other words, your p-value is smaller than your significance level. But in the big scheme of life, the practical significance is irrelevant. Sometimes the test will miss and say you're not statistically significant because your p-value is bigger than your significance level. But in the real world, there was practical significance. And so you can go both ways. The test can tell you statistical significance, there is no practical significance. The test can tell you no statistical significance, but there is some practical significance. Both of these is a story about, what is that? That's the standard deviation of the sampling distribution of our sample mean x bar. This becomes a problem in one of two cases. When the sample size is very, very large, or when the sample size is very, very small. Right? So my thought is this. When n is large. Now, I'm not talking large being 1,000 or 500 or 5,000. I'm talking about the sample size being 50,000, 100,000. If the sample size is large like that, in other words, you've taken a sample of 50,000 people, the problem is going to be the sigma over the square root of n is small. Why? You're dividing by that gigantic sample size, right? You're dividing by the square root of 50,000 or the square root of 100,000. What happens in this case, where your sample size is just so gigantic, and I will give you, larger samples do give you more accurate results when you're looking at a confidence interval, right? Because they make the margin of error smaller. Large samples here are a problem because what's going to happen is, since that standard deviation is small, what the test is going to tell you, you'll have statistical significance. In other words, the p-value will come back and be smaller than whatever significance level you're looking at because your standard deviation, sigma over the square root, is so small. Problem is, the test is going to say, yeah, you're looking at statistical significance result, but no practical significance. While you're writing, I'm going to tell you this. Just for the sake of things, suppose that standard deviation of the population is like 5, right? And you've taken a sample of 50,000 individuals from your population. When you look at 5 over the square root of 50,000, that's going to be very small, right? You know, like 0.000 something, yes? So, if your mean, maybe you've assumed that mu should be 10, right? And just for the sake of things, let's say we've made everything work out. My sample size is so large that that standard deviation is 0.001. I'm sitting here at 10. If I go to 10.003, how many standard deviations away from the mean am I? 3, right? Is that a large test statistic? Yeah. Is that going to give me a small p-value? Yeah. In other words, you're only off by 0.003. The test is going to say, your statistical significance. What am I looking at? That's 3 10,000ths, right? Is being off by 3 10,000ths got any practical significance to it? Hell no. The United States government, everybody will live with 3 10,000ths, right? Any manufacturer would live with 3 10,000ths. The problem is your sample size was so large, well, hell, 3 10,000ths shows up to be statistically significant. Now, I didn't think much about this, but I was sitting home and watching TV once. And I say once because I don't watch TV all the time. I don't have cable, but I did have cable at this point. And there was a guy on the news, and he was from Toronto. And what he was studying was, true story, he was studying cell phones causing brain cancer by the year. And he had done like a nice randomized comparative experiment. He had all the magic work. And he'd done an experiment maybe on 500 people. And it turns out he didn't find any statistically significant result. In other words, between the cell phone use and brain cancer. You know what the dude said on national TV? He said, it ain't a problem. I'll just keep increasing my sample size, and then eventually I will get something that's statistically significant. What's he talking about? I don't care what your standard deviation sigma is. If you'll let me take any sample size large that I want, I'll make anything show up to be statistically significant, but there won't be no practical significance. The other side is also a problem. And what I mean by the other side, when n is small. Now I'm talking like you took a sample of size 2, or you took a sample of size 3, maybe even a sample of size 4. The problem is your sample size is so small that standard deviation is still rather large in the big scheme of life. So the problem is, your sample size is so small, that standard deviation is still so large, the test ain't going to pick up shit as being statistically significant, and there's all kinds of practical significance running all over the place. In other words, when the sample size is small, the standard deviation is still large, no statistical significance. The test is not going to find anything. It's going to tell you the data is consistent with the null hypothesis being true. No statistical significance. The problem is, there is practical significance. the test just can't pick it up. You didn't take a large enough sample. That standard deviation is still too large to know for it into the test to pick it up. Now, I'm going to read this little box to you on the bottom of page 418. That's where all this is at that I'm talking about. I've given you the highlights here, but you want to look at this box on page 418. And it says, the sample size affects statistical significance. Because large random samples have small chance variation, very small population effects can be highly significant if the sample size is large. That's this page. Right? They're talking about sigma of the square root n. That variation, that spread, that standard deviation is still small. Because small random samples have a lot of chance variation, even large population effects cannot fail to be significant if the sample size is small. That's this page. The test won't pick it up, even though there's some practical significance. Then what's the last line say? Statistical significance does not tell us whether an effect is large enough to be important. That is, statistical significance is not the same thing as practical significance. The statistical significance is just coming from the test. That's all. And it looks like, I'm not supposed to say this out loud, my statistician friends get upset with me, but it looks like I can manipulate this. By the sample size, right? Obviously, I start taking a large sample, hell, I can make everything statistically significant. And if I'm not paying attention to what I'm doing and I take too small a sample, well, hell, my test isn't going to pick up anything that it should be picking up. Right? That's the problem. Now, here's the problem me and you need to be able to calculate out of here. There's one calculation out of here. And my calculation is this. Choosing the sample size. Now, remember my sample size is always in. So here's what I've got. Before I ever do anything, I'm going to fix a confidence level. In other words, I know what confidence level I want to use, whether it's 95%, 90, 99, whatever the hell it is. And a margin of error. Remember, the margin of error is denoted in, that we can live with. Now, this is before you ever start trying to calculate your confidence interval. If I know the confidence level I want to work at, and I know the margin of error I can live with, then I can find your sample size. How? Remember, the margin of error is this. Remember the plus or minus part in your confidence interval? What I want to do is I want to solve for your sample size. Well, when you do that, I'm not going to sit here and show you the algebra. That's not what's important to us. I'm going to get this. It's on page 421. You don't have to memorize it. It's on the formula sheet. Choosing the sample size for where you're trying to estimate a population mean and sigma is given to you. Here's the deal. I got to have both of them. I got to know the confidence level I want to work at. I got to know the margin of error I'm willing to live with. Okay? So I don't want to look at example 18.5. You can look at that one. I'm going to flip the page. And I would like to look at 18, it makes no difference here. I'm going to need your help, but I'd like to look at 1812 on page 422 to see how we do this. It says this, example 16.1 on page 377, assume that the body mass index, BMI, of all young women follows a normal distribution with a standard deviation of 7.5. Population distribution is normal. I'm going to put number 1 there. And then sigma, was 7.5. Right? I always like to keep track of my simple conditions wherever I'm at. Now, I'm going to give you check marks here. I haven't read anything that tells me about a simple random sample yet, correct? Because it says How large a sample would be needed to estimate the mean BMI mu in the population to within plus or minus 1 with 95% confidence? The reason is they want you to find N for C being 95% and M being, oh, I know your book says that the margin of within plus or minus 1, that's the plus or minus part, right? The 1 is your margin of error there. So they want me to find the sample size. So nobody's going to tell me this part. That's not what we're looking at here, right? I need to find N. Well, what's my formula? My formula is please don't forget that little 2 on the outside. Because I guarantee you, if you've got to do one of these on the final, without squaring it, the answer will be there. It just makes a good, easy, wrong answer for us to do. That's the deal. Now, where does Z star come from? Z star is from table C at the bottom. In this case, Z star is 1.96, correct? Everything else we need is looking at me. Sigma 7.5, M, your margin of error is 1. So N is equal to 7.5 times 1.96. I need somebody that's got a calculator to tell me what is this number. What is 7.5 times 1.96 divided by 1? And then whatever you get, would you please square it and tell me what N needs to be here? Point 216.09. So that's exactly like 2 decimal places here, correct? Now I'm going to give you, obviously I can't choose 216.09 women, young women aged 20 to 29. So what we always do is, normally people would think, you just, how you round. I'm going to put it in red. We always round up. Even though that's 216.09, we are going to round up and we're going to say we need to take N equal to 217. Always go to the next whole number. How's that? Even if that was 216.0009, I would go to 217. And the reason for it is, if we were required to have 216.09, but we go to 217, when you actually calculate your confidence interval at 95%, the margin of error will actually be smaller than 1. And everybody can live with your margin of error being smaller than required. We can't live with the margin of error being larger than required. In other words, always rounding up, the statistician would tell you this is conservative. Meaning the margin of error will turn out to be a little bit less than what was required, and everybody will be happy. Everybody gets pissed off when your margin of error is a little bit bigger than what was required. Just chopping off the 0.09, it would be a little bit bigger than 1. No. Going to 217 makes it a little smaller. Now, here's my thing. One of the homework problems is one of these. And I think it is, just to get you, it's 18.42, right? That was one of the ones I asked you to do on page 432. How large an SRS or untrained students do you need? The margin of error will be there, the confidence level will be there, the signal will be there. You're going to plug in, that's your formula right there. N is equal to Z star times sigma rand. And please don't forget the squaring part, right? But we do the inside and then you square it. Now, I'm going to say this is probably like my last thought here. Yeah. This whole chapter. I kind of want to see how we do with this part. And what I've got is this thought. All right? There's something called type 1 and type 2 errors. And here's what we're going to do. We're going to use, we think about this when we're using a test, a hypothesis test, test significance, to make a decision. At significance level. Now, one of these we would have done already. Making the decision one way is always fine. We never ever did pick and say, I never said to you that if my p-value was large, in other words, I didn't have significant results, that the H0 was true. All I would ever tell you was that the data is consistent with H0 being true. We didn't pick that. All right? Now, I'm going to do this. One, we would reject the null. And if you're going to reject the null, you're going to accept the alternative as being true. You would do this exactly when you have statistically significant results at the alpha, significance level alpha. Right? All I'm saying is, you've got statistically significant results, we will reject the null and accept the alternative. Now, number 2 needs a little talk here. Accept the null as being true exactly when you do not have statistically significant results at your significance level. We would have never done this before. When I fell to this part here before, I would have told you, you don't have statistically significant results, the data is consistent with H not being true, but I would never say we're going to pick the null to be true. That would have been a no-no. But when we're going to make a decision, you have to pick the null or the alternative, and this will tell you when you're going to pick which one. So, the problem is when you make a decision like this, and you pick one or the other, we make errors. Unfortunately, the test of significance is not perfect. A type 1 error is to reject the null. That means you're going to accept the alternative. The problem is, you're going to do that when H0 is true. The test is telling you to reject the null and accept the alternative. The problem is, H0 is actually true in the population. Mu is equal to some value. A type 2 error is, here you accept the null. The test is telling you, oh, you did the test, your p-value is bigger than your significance level. You're going to accept the null. The problem is, the alternative is actually true in the population. I'm going to draw you a little diagram, but that's your definitions here. Where are these definitions at? These definitions are on page 425. And then I got one last thought here. People always want to talk to you about the probability of a type 1 error. What's the probability that you'll actually reject the null when the null is true? Well, it turns out this is very, very straightforward. That probability is whatever your significance level is. Because when do we reject the null when the null is true? That's exactly your significance level. When you are far enough out the tail. Nobody's ever going to ask you about what's the probability of a type 2 error in this class. That's just way beyond our scope. Now, I want to draw you a picture of what's going on here. What I've got is this. I'm going to draw you a little diagram of this. There's 4 boxes in my diagram. Alright? And what I've got is, up here is the truth about the population. One of two things is true. Either H naught is true, or the alternative is. Obviously. On this side is the decision based on the test, or if you like, the decision based on the sample. You're either going to reject H naught, or you're going to accept H naught. Now I'm going to write in red. You're going to accept the alternative up here. But that's kind of like a given. We always think about what you do about H naught. Do you reject it or do you accept it? Well, if you reject it, you're going to accept the alternative. Now, you see this right here? This is correct. That's a correct decision. If the test tells you to reject H naught, to accept the alternative, and the alternative is true, now that's a correct decision. You see this one down here? That's correct. If the test tells you to accept the null, and the null is true, obviously that's what you were supposed to do. Right here is your type 1. You reject H naught, you accept your alternative. The problem was, the truth about the population was that the null is true. Here is your type 2. The test is telling you to accept the null. Problem is, the alternative was actually true. All I'm doing here is I'm trying to give you something that you can remember. That right there is what's in words, right? You reject H naught when H naught is true. Accept the null when the alternative is true. That's what we're doing over here. I don't know which one is which. Will help you the best. Which one will make you remember this. Now, I've got two places I'd like to talk about this. And it turns out for me, it doesn't have anything to do with, a mu this or a mu that. I wanted to think about this in terms of it turns out a jury trial, it's a test of significance. People don't think about it like that. But the null is that whoever's on trial is innocent. What's the judge say when we start? The person is innocent until proven guilty, right? So what are we assuming? We're assuming the person is innocent. What's the alternative to being innocent? Person's guilty. Now, where does the evidence come from? How do we know, when are we going to reject the null and accept the alternative? Well, it's when the lawyers are the ones presenting the evidence, right? And when the evidence is beyond a reasonable doubt. All right, I got to think about it like this. When it's really far out the tail, from here, right? There's so much evidence built up of beyond a reasonable doubt. From here on out, we're going to say the person is guilty. From here on back, we're going to say the person is not guilty, right? When the evidence is not beyond a reasonable doubt. Yeah? Yeah, there's no numbers to be put there when we do a jury trial. Yeah? Does a jury trial make errors? Oh, all the time. What's type 1 error with a jury trial? What does it mean to reject H naught when H naught is true? What the jury trial does do? You just told me that an innocent person is said to be guilty. That's a type 1 error. What's it mean to reject H naught when H naught is true? You're accepting the alternative. The jury trial is telling you that the person's guilty, but the problem is, the truth of the matter is, the person is innocent. What's a type 2 error? What does it mean to accept the alternative when... What's it mean to accept the null when the alternative is true? Oh, this is the bad one too. What did you just do? Guilty person I always have a hard time when the jury trial comes back and says, you're not guilty. I have a hard time saying that you're innocent. You're just not guilty. The evidence wasn't beyond a reasonable doubt. Now, I always like to ask students this question that we're here. So a type 1 error in a jury trial is an innocent person is guilty. A type 2 error is the guilty person is not guilty. Which one of these errors is worse? Come on, me and you got 2 weeks left. You know that's the kind of question I'm going to ask. And my answer is going to be, it depends on if I'm the person on trial or the person that is next to the person that's on trial. Because if I'm the person on trial, type 1 error is the worst. Sending my innocent person, sending me innocent to jail, that would be a problem. Of course, I could appeal. But if I'm living next to the person that's on trial, which one's worse? Well, sending that guilty person back to me that then killed 6 people, that would be a problem, right? It all depends on a person's perspective. Nobody's going to ask you that. The point is, do you understand what a type 1 error is and what a type 2 error is? What does it mean to reject H0 when H0 is true? What's it mean to accept H0 when the alternative is true? There. There's one other place I was thinking. Now, they don't use the terms type 1 and type 2 error, but medical testing, where you're testing for some disease, right? So, I'm going to give you the null is the person is healthy. The alternative is the person has whatever disease you are testing for. Now, if I flip-flop these, you understand it's going to change what I'm getting ready to tell you about type 1 and type 2 errors, but we should still be able to write it down no matter which way you go. See, I can't flip-flop these. As I just told you, what's the judge tell you to assume to be true? The person's innocent. I'm medical testing for some disease, right? So I'm going to assume that starting out here, the person's healthy. The alternative is the person has a disease. It could have went the other way, right? The jury trial, I can't go the other way. What's a type 1 error here? What's it mean to reject H0 when H0 is true? Says a healthy person has the disease. That's not overly comforting. Right? So type 1 error is to reject H0, reject the fact that they're healthy, but the problem is you're going to tell them they have a disease, but all reality is they're healthy. And then there's a type 2 error here. What does it mean to accept the null when the alternative is true? It says a person with the disease is healthy. That's what it means to accept the null when the alternative is true. Now, medical testing, they don't talk about type 1 and type 2 errors. What do they talk about? False positives, false negatives. Which one of these is the false positive? All right, the test comes back positive, says the person has the disease. The problem is they don't. Which one's the false negative? I thought there's only one left. The test comes back and says the person's healthy. The problem is the person actually has the disease. Which one of these two is worse? Again, depends on what side of attention. If I'm the person you're testing, I'm pretty sure the false negative is the worst thing to happen. Because what happens with the false negative is the test comes back and says you don't have the disease. What do? You send the person home, you never test you again. If it comes back as a false positive, what do? They keep you in the hospital, they test you again, they eventually figure out you don't have it. Yes? What about you're next to the person that's living with whatever disease is contagious? The other one's what? Now, those are my two types of type 1 and type 2 error. That's just the way I think about them. please, when you go home, would you please read chapter 18? Please fill in all the little pieces that I didn't say. I've talked about almost everything that's there. The big thing you want to remember is we have very powerful tools. Confidence intervals, test of significance. They're not powerful enough to fix bad data. All right? You need to understand the difference between statistical significance and practical significance. You need to be able to choose a sample size for a confidence level and a margin of error. And you need to be able to identify what's a type 1 and type 2 error. Now, I know I should let you go. I'm not going to because we need to talk a little bit more. I am going to start skipping chapters. You know, from the beginning of the semester, I went straight through the book, right? But now that I've finished chapter 18, I'm going to skip a couple chapters, and I'm going to skip closer to the end of the book for a reason. There's only one more chapter that me and you are going to calculate things by hand, you know, with the calculator and by hand. And I would like to do that before I come back, and all I'm going to use on you is the software. What's going to happen in the last 3 chapters that me and you do? There's one that we're going to do by hand. There are 3 chapters that we're going to use the software. So there's a couple things we've got to be able to do. We've got to be able to read the printout. And then you've got to be able to interpret what you see. Then you've got to be able to check to make sure whatever in the hell I'm giving you, should I be allowed to use it? In other words, are conditions met? Right? But then this other chapter, I'm still going to go and I'm still going to do things by hand. And it's chapter 22. So I'm skipping over a few chapters. I just want to get you started on this idea that I'm getting ready to change some things up on you. And chapter 22 is inference about a population Now, when I write, we're looking at inference about a population proportion. I'm getting ready to change your parameter. In other words, I'm getting ready to change that unknown quantity about a population I want to know about. And I'm going to give you, obviously, you have to change the statistic you're going to calculate here. Now, here's the way I want to think about everything in this chapter. I'm thinking about the proportion of some outcome, whatever it is, in a population. This outcome I'm thinking about, I always want to think about it in a certain way. I want to think about the outcome as a success. I don't care what the outcome is I'm looking for in this population or the proportion of that outcome. I'm going to think about that, the proportion of successes in that population. And if it's not a success, anything else will be called a failure. Right? If it's not the outcome we're looking for, a success, everything else will be a failure here. Now, I would like to take a look at example 22.1 to get us started with this idea. It says, how common is behavior that puts people at risk of AIDS? In the early 1990s, the landmark National AIDS Behavioral Survey interviewed a random sample of 2,673 adult heterosexuals. Sample size. And this time you're looking at adult, heterosexuals, okay, and they asked them a question. Of these, 170 had more than one partner, sexual partner, in the past year. 170 more than one partner. I'm almost tempted to write up that that would be the success I'm looking for, that the person had more than one partner, but not everybody will take kindly to that. So I won't write success here, but I'm thinking about there's 170 successes. Right? Now, it says that 6.36% of the sample, how did they calculate that? took 170 divided by 2673. Where's the 6.36% come from? Through the decimal place. See, here's the thing. All of our work is going to be done in terms of the proportion, 0.0636, or whatever proportion we're looking at. Nobody wants to hear about your proportion. Everybody wants to hear about the percentage. So we move the decimal place 2 to the right. Okay? Now, that's what this chapter is about. It's trying to do inference for a population proportion. The proportion is something we can think about as a successful outcome in your population. Well, the thing is this. There's something called the sample proportion. That's read as yeah. That's your statistic this time. That's what you're going to calculate from your sample. How do I know that? It says the sample proportion. Just like previously we had the sample mean, right? X bar, that was your statistic. That was calculated from your sample. Now, your parameter here in all of these problems is going to be some unknown population proportion, and the notation we use here is, those are all lowercase, right? So that's a lowercase p. That's going to be your population parameter. It's going to be some unknown population proportion, right? Some unknown proportion of successes in your population. Now, again, your statistic is your sample proportion. P hat. So, in the example we were just looking at, just for the sake of things, in the example we were looking at, whatever that was, example, what was it, 22.1, okay? The population there that you're looking at is all adult heterosexual. What was the proportion you were looking at? P, your parameter, lowercase p, is the proportion that had more than one partner. In the past year, I'm not going to write that. That's your parameter, folks, right here. This is your parameter. That's the unknown quantity we want to estimate. So what did we calculate? Oh, well, hell, we calculated that sample proportion. I didn't write it back there. Right? We calculated the sample proportion, p hat, and how did we do that? We took our 170 that had more than one partner out of your sample, and then we divided by the sample size, which was your 0.0636. Right? How am I always going to do this? This time here, this is my statistic. This is what got calculated from your sample. In general, how do I calculate p hat? P hat is always the number of successes, whatever outcome you're looking for. Remember, we're thinking about it as being a success. Number of successes in the sample. Can I just do this? What are we dividing by? I'll do it like this. N. You're going to divide by your sample size. That will give you your sample proportion, your statistic, your p hat, however you want to think about it. One last line. I know I'm supposed to go home. I know. It's frickin' Thursday. The weather's nice. It's 6:51. I got to write one last thing. We're going to use p hat estimate P. We are going to use our statistic to estimate our parameter. Please get that stuck in your head. That's what we do all semester. Use your sample proportion to estimate your population proportion. Use your p hat to estimate P. Use your statistic to estimate your parameter. Now, on Tuesday, what we have to talk about, and then I'm done, I'll shut up. We have a new statistic. We need to talk about the sampling distribution of. In other words, I want to know what happens as I go from one sample to the next. What's the distribution of values look like of the sample proportion of all the samples of the same size from the same population? In other words, we've changed our statistic because we've changed our parameter. Be careful going to the house. Do not forget my homework problems that are due on Tuesday. We will pick up right here on Tuesday next week.